Yeah, let me start the session here. So our next speaker is Ankit Sharma. He's a system architect at Steradian Technology, and he's a graduate from IIT Madras, specializing in signal processing and wireless system. And he was the systems engineering lead at Freescale India for one of the world's first LTE base station SoC. And currently, he has authored 2 IEEE journals, 4 IEEE conferences, papers, and has issued 4 US patents. And over to you, Ankit.
Thanks, Chetan. Hi, I am Ankit, as introduced by Chetan, and I'm representing Steradian Semiconductors here from Bangalore, India. And today we are going to speak on a topic called learning for enhanced vision. Just to introduce ourselves as a company, Steradian Semi, we were founded in year 2016. We are a product-based company making complete 4D and soon 5D imaging radars. Our market focus remains on automotive and industrial both. And we are complete end-to-end solutions provider for millimeter wave imaging radars. And we have multiple patents towards north of 15, as mentioned here. Brief intro on the product. We have a Steradian's radar module. This is one of the radar modules that we have, offering a sub-degree angular resolution, that is for the direction of arrival estimations that has to be done by the radar. Nearly 0 false alarm rates, and a very rich and high density point cloud. The echoes that come off from the objects are typically known as point clouds in radar parlance. The unit itself is completely software configurable and runs for all the modes as long range modes, medium range modes, and short range modes just by a mere change in the software command. A very wide FOV, that is the field of view, from plus 60 to minus 60 degrees in azimuth and plus 15 to minus 15 degrees in elevation. We offer a very high dynamic range. This typically enables you to detect vulnerable road users, typically a pedestrian or a child, in presence of very heavy objects like a guardrail, metallic pillars, or trucks, or heavy cars. Okay, so now we move into the hardware-software architecture that our solutions offer. And probably later on, we'll leap into how tinyML fits into this imaging radar world and what at Steradian do we do about it. So let me, to set the stage, let me give you a brief introduction about the hardware-software architecture that we follow here at Steradian. And so the complete radar system architecture can be divided into very broadly into 3 blocks, starting from the left-hand side. I think I'll use my pointer for a bit. Sure. Starting from the left-hand side, the radar hardware, which itself is composed of the front-end ICs that gather the data for you. They transmit the pulses and gather back the echoes from the objects, digitize those pulses and send it to a signal processing block. And the signal processing block further pushes out samples to a perception layer. By perception, what we mean is how do you want to visualize those echoes that the radar has echoed for you. Our radar front-end IC is in partnership with Renesas. Right from the hardware itself, we have a very open architecture in which the number of ICs needed per application can be selected. So, for example, for an autonomously navigating agent, you may want to have a very high density point cloud, right? But for other cases like intelligent transportation systems or speed enforcement systems, you may not be wanting that, right? What you would just want is the accuracy of the speeds of the vehicles that the radar is reporting. You can tune down this end to maybe a 1 IC or a 2 IC solution like that. Then we move on to the signal processing unit. The signal processing itself is a system stack, which is very open, and component library based system stack, which is capable of running on an off-the-shelf x86 processor, as well as on specialized NVIDIA GPU processors. And out comes the perception layer output, which is composed of the process point cloud and tracked objects, where we are tracking objects in real time and reporting several features of those tracked objects. Okay, so what does tinyML have to do with imaging radars, right? We'll just delve into a little bit of radar literature. So what does a radar typically measure for us? And we'll talk about 4D radars. So the range, the elevation angle, and the azimuth angle is well known. That forms the XYZ of whatever the radar detects. Plus, since it's a Doppler radar, it also measures accurately the speed of the moving objects. So that's how we form the 4D imaging stack of a radar, which is composed of range, both the elevation, both the angles, and the radial speed. In building this into an imaging radar quality product, there is a very fine interplay between how we measure the range and the velocity both. So ideally, what we want is for a radar to be placed well in all the corners. We want the radar to be able to see the farthest. We want the radar to be able to detect the max velocity. 350 kilometers per hour is today becoming the norm. We also want the range resolution to be very, very fine, right? We want to be able to detect in very fine steps of range. And similarly, we want a very high velocity resolution also. As listed here, there is a very fine interplay between how high in RF bandwidth can you go, how fast can you sample your samples once they are echoed, how fast can you chirp? Typically, the pulses that the radar sends out are called chirps. How fast can you chirp? And at Steradian, we have revolutionized this, and we have come out with proprietary schemes that ensure best-in-class range and Doppler resolutions, plus the max parameters. So we spoke about the radar system architecture, the range and the Doppler aspect. And when you put the system together, this is just to give you a glimpse of what you get. Starting from the top left corner, you can see very finely constructed shapes, and you are able to spot something like small traffic cones. Those 4 traffic cones are very finely reconstructed over here. You are able to estimate postures to humans playing football. You are able to estimate the poses. You can see a humans with hands spread, the head and legs, a vague shape of the hand and legs also. And much hyped about elevation. You can see a big ladder over here, which is very finely reconstructed in our radar point cloud also. So what do we do if we get such rich feature sets from an imaging radar, right? What should be the logical next step? The logical next step, as mentioned over here, is the feature-rich radar point cloud enables a classifying agent which sits right at the intersection of machine learning and fundamental signal processing. So this gives your radar a more camera-like ability to sense the objects and then be able to learn from the features and be able to classify objects and say, this is a pedestrian and this is a car, right? Or several distinctions like those. Moving on with classification, object classification, and traditionally it has been done visually using cameras, soon going to be replaced. This is just a comparison of how traditional radars, the 1D, famously called 1D radars, the camera, the LiDAR, and how a system of 4D plus camera compares with all these systems. It's clearly very evident that the 4D radar plus camera beats all the other combinations by margins. Typically, LiDAR is a contender, but there are several cost factors, and there are also weather factors. The LiDAR cannot, at least till now, it's not been an all-weather device, and lighting conditions and the weather conditions can severely impact the performance of the LiDAR. So it looks like 4D radar plus camera is kind of a system where you sense and you also get this fifth dimension of classifying objects. Yeah, we'll soon, maybe very soon in future, this system can be replaced with a radar alone, which preserves the privacy aspect also and is able to classify objects on the fly also. That's what we are attempting here at Steradian. Let me give you a brief glimpse of, let's say this is a figure sensed by, or this is the point cloud sensed by the radar, right? And you can roughly maybe not be able to imagine what exactly the scene corresponds to, but yes, roughly you would say, okay, these are something like grills or guardrails. There is a free path between those guardrails. And then this looks something like a high-rise, some flora, fauna, some trees or something like that. But yeah, it's very vague, right? Maybe better for a machine to understand this than a human eye. What a human eye understands better is this camera image, which is actually sensed by the radar like this. So these two are corresponding frames. One is a camera frame and the other one is a radar frame. And why the human eye relates to this is because human eye has been mechanized to recognize that this is a bike and this is a tree and these are guardrails, right? We are also, the eye has also been trained into recognizing these. What we say then is the camera and radar are complementary sensor technologies. Radar forms a very solid foundation for an all-weather lighting independent sensing, whereas camera is still needed to do stuff like reading signboards for an autonomously navigating agent, read signboards, recognize number plates for speed enforcements, and all other kinds of visual identification activities. At Steradian, our SRIR 256 and 144 5D imaging radars enable the fifth dimension actually, and we are now today being able to classify objects on the fly using just the radar point clouds. Putting this system together, yes, one can say that the much coveted L4 autonomy looks to be very achievable, right? Before moving on, we'll quickly run through some applications. These are some of the applications that I just showed. Free path mapping can be done. So that allows you to do path planning using radars. You're able to classify what is static, what is moving, and be able to better plan your path. You're able to reconstruct shapes like almost like a camera. You can see these high metallic grills over here, which are very faithfully reconstructed by the radar. You can see the color by height, and the complete top to bottom is quite faithfully reconstructed. There are applications of in the domain of intelligent transportation systems, speed enforcement and whatnot. And today, as we speak, our radars are actually monitoring on Indian highways and monitoring till the distances of 250 meters and detecting any violations of speed using our radar. Similarly, detecting humans, as we said earlier, very important for an autonomously navigating agent. And the better part is that we are able to detect humans and classify humans in presence of very strong objects like metallic grills and big cars, right? Okay, so what does object classification entail and how do we deal with it at Steradian? For object classification for radar can have many applications, and it's not possible to cover all those applications today, but we'll focus on the most important ones, which are the intelligent transportation systems and autonomous navigation. And to be able to do that all, of course, you need a 5D imaging radar, the fifth dimension being the class of the object, and you need a camera. You need to be able to detect traffic lights and be able to respond corresponding to the signaling. You need to be able to identify the markings on the lane and be able to take appropriate action. You need to be able to localize yourself, right? Parking lot detection, one very important per se imaging radar application, and only imaging radar. I mean, we are not very far away from the time where imaging radar alone will be able to do this, which is vehicle type detection for speed enforcements, because speed violations are different for different vehicles. Or maybe for a truck or for a very heavy commercial vehicle, it will be much lower than a passenger car. So the radar needs to be able to make out what kind of vehicle it has detected and be able to impose the violations accordingly. VRU is vulnerable road user, and we have already spoken about it. It's very important for the radar to be able to distinguish this. Okay, so how do we make this possible at Steradian? We'll quickly go through that. So as we spoke about the system stack earlier, which is a kind of a complete stack that gets the digitized sample from the front-end ICs and processes these samples to produce a very rich feature set, right? Famous terms are RCS, which is called the radar cross-section, the SNR of the echoes that you get back, the position, the heading, and the dimension. And there are various other features, just listing some of them. All these features are compiled into an n-dimensional feature vector, which we call the radar feature vector. This is then fed as an input to a supervised learning agent, which runs in a higher dimensional space. And out comes the pattern classifier. And as we speak today, our radar on the road is able to classify, put 3 classes to the vehicles that it detects, which we call the two-wheeler or the bikes, the small four-wheeler or the cars, and the big four-wheelers called the trucks and the buses and all the heavy commercial vehicles. Why we specifically call it tiny and why we really think it is tiny is because once we compare it with the available literature, the state of the art, let's say a radar transformer, which is a very deep layered neural network that does the classification for radar point cloud. The problems with such model is that the training data requirement itself is huge. It's extremely inconvenient to collect such volumes of data on roads, right? And then, of course, the story doesn't end there. You have to follow it up with extremely long cycles of training and tuning. And of course, the space complexity remains high. We just contrast it with our own model that we have built. And quite literally, we have made the distinction of not treating the radar point cloud as camera pixels, because that's where most of the literature tends to go. We do think radar point cloud has to be classified on the basis of radar features only and not necessarily in tune with visual classification. So at Steradian, we have a very precise and rich feature set, which we already spoke about. The training models are rightly placed at the intersection of fundamental signal processing and ML to borrow as much from ML as is required and not overdo it to build them into heavy neural networks. And today we are delivering a 3-class accuracy of 95% on Indian roads. On the fly, when a model predicts, we have prediction complexity, the big O complexity, which is, you can already see linear in the product of the test samples into features, which is quite in contrast from neural networks. Of course, different neural networks will have different complexity, but all of them, maybe the lower bound can just be placed at let's say the number of layers cubed, the complexity, right? Which becomes quite a challenging task when you have to do something as real time as traffic monitoring, where you are detecting vehicles moving at 150 or 180 kmph, and you have to catch back the echoes, process them, send them back to the control center, and do all this process in a very limited time frame. Just a fair comparison, our model more easily generalized because we've trained it on radar point cloud itself, in contrast with state-of-the-art models that tend to borrow from a visual classification. The training data requirement itself is much lesser as compared, again, with the neural networks. The training time is close to just mere 30 minutes, and that too on off-the-shelf x86 processor, which can take quite a long time for available neural networks, as we know, on a similar processor. That doesn't end there. We have a functionality to shift this over to, let's say, parallel processing GPUs or something, and get this down to, let's say, a sub-minute training time, which will really make it tiny in the true sense. And online predictions, of course, we've already seen. Using off-the-shelf edge processors, these predictions have to work on the edge most of the time. And that's why we make this model kind of cut out for these kind of applications for radar-based classification. We have some results to share using this model that we have prepared for radar point cloud-based classification. And currently, as we compare ourselves with available literature, state of the art, this is how we stand. A little bit lower on the big four-wheelers or the trucks or the HCVs, the heavy commercial vehicles, which we know the limitation and we are working on for the next drop of our release. And the story doesn't end there. We are trying very hard to push the 3-class limit to a 5-class and eventually 7-class classification labels. This is a small, we thought a demo video may convey a lot of more information than mere words. So this is a video that we're going to play, and this has a lot of information embedded as far as the point cloud quality, the richness of the features, and specifically we take you to a section where we have actually deployed this system on Indian roads, and you can see vehicles being monitored, their velocities being monitored, and they being rightly classified on road. Chetan, could you let me know once you're able to
Yes.
hear the audio and see the video?
Yeah, right now it's not. You need to remove the laser pointer and then probably it will have, yeah. Yeah.
That's about the demo.
Yeah.
And quickly moving to what we think would be the way forward here for us, as well as for a lot of people who are trying to do classification based on radar. So essentially, we do not want to overdo neural nets to the tune that we are not able to run them on the edge. Our belief is that radar point cloud classification has to lie at the right intersection of signal processing and machine learning. That's what we are vying for. And of course, the way forward is that we want to encompass more classes, right? We want to maintain the compute on, let's say, an off-the-shelf or a kind of a nano platform. And of course, we want to maintain the generalization so that the same classifier or the same agent works equally well for both, let's say, an ITS or an automotive scenario. With that, I think I come to the end of our talk here. And for any questions, even offline, you can connect at the given contact at steradiansemi.com. Thank you very much.
It's a great talk, Ankit, and the video was amazing. And we are running out of time here. So let me see if there is any more questions here. Let me just ask one last question here. So since you're using radar, right, and you might have seen this, it's all point cloud, right? And very sparse data. So are you handling this sparsity somehow in your data so that your computation would be smaller or would be power efficient right now?
That's right. That's right. By the design of our radar, the MIMO array itself is laid out in a sparse manner. And you rightly mentioned we are borrowing heavily from sparse signal processing to do the direction of arrival processing.
Yeah, but for neural network, you might be creating some features, right? So what those features are sparse, or from that point of view I was talking about?
Currently, for classification, we are not using sparsity of the feature set per se, but that's a good point to look ahead in the future for.
Great. One last question from our audience is this device compatible to ADAS? If yes, what is the data interface?
ADAS, yes, it is compatible, and I think mostly are you talking about a CAN interface? Yes, if that's the question, yes, it does support CAN interfaces.
Great. I think we'll just close the session. Close this talk here. Thank you, Steradian and Ankit, for a great talk. Yeah. Thank you.
Thank you.
I also want to extend our gratitude to all the tinyML strategic sponsors who made this event possible. At the executive sponsorship level, we have ARM, my old employer, who provides the software and the hardware foundation, tinyML. Edge Impulse is the tinyML platform for all developers. Qualcomm advances AI research to make efficient AI ubiquitous. Sentient offers end-to-end deep learning solutions for tinyML and Edge AI. At the Platinum sponsorship level, we have Reality AI adds advanced sensing to your product with Edge AI and tinyML. Renesas, who has big ideas for every space. With our golden sponsors, Latent AI develops adaptive AI for the intelligent edge. Maxim Integrated, who is now part of Analog Devices, enables edge intelligence. Seed Studio, they are the IoT hardware enabler. tinyML builds smart IoT sensor devices from data. SynSense builds sensing and inference hardware for ultra-low power devices. We will have some special partner sessions in the next few days, led by the sponsors we just introduced. At the silver sponsors level, we have Aeon Devices, Deep Light, AMSA Vision Sense, Green Waves Technology, Gravity, HOTG, Imagine Mob, Kixel, Rexin, and SAP.